Everyone, I'm Bohan Zhang. I'm a member of technical staff at OpenAI. In this talk, I will discuss how we scale Postgres to the next level at OpenAI. Specifically, we will talk about how we operate Postgres and the lessons we learn and the challenges we face and how we address them at OpenAI. If you are a DBA operating a production Postgres at a very large scale, you might be interested in this talk. Okay, let's get started. Let's see what we did at OpenAI to scale Postgres. So before starting the talk, I would like to acknowledge my the hard work from my teammates. Thanks Siqing Liu, Chaomin Yu, Chenglong Hao, Ben Rice, and more people in the OpenAI infra team. Thanks for all their hard work to make Postgres super reliable and scalable at OpenAI. A little bit about myself. I am a member of technical staff at OpenAI. Before that, I was a co-founder at Otterton. Which is a Samuel spin-off, based on many years of research from Carnegie Mellon Database Group. So we basically apply the machine learning and AI approach to automatically optimize your databases, specifically optimize Postgres and MySQL. And before Otterton, I was a researcher at Carnegie Mellon Database Group, working with Professor Andy Pavlo on the Otterton research project. Background. So Postgres is the backbone of our most critical system at OpenAI. So if Postgres goes down, many of our key features will become unavailable. So Postgres failures have previously led to multiple self-zero outages, which take down the entire ChatGPT service. So Postgres is super important at OpenAI. So scaling Postgres to meet OpenAI demand is also super important, but it's also non-trivial. It's not an easy task. So historically, we operate on a single primary instance in Azure without sharding at all for a very long time until we encounter the raw scalability limits. Since if you only have one single primary, you cannot scale RAS horizontally. So in a single primary multiple replicas architecture, RAS scalability can become some bottleneck. So for the re-queries, you can add more replicas to scale rates. But for the RAS, we only have one single primary. So this architecture actually, in this architecture, the RAS scalability is a bottleneck. We did lots of optimization to make it work. First of all, we moved most of the read-heavy workloads to other systems. So we migrate off the write-heavy workloads from Postgres. We also make sure new tables and new workloads are not allowed, which means that we only support the current workload. We don't want the new write traffic to the current setup. We also did lots of optimizations to ensure the current architecture has sufficient runway to support existing read-heavy workloads and future growth. We'll discuss that what optimization we did in the next few slides. But right now, we have a sufficient runway in the current single primary setup. What we found is that Postgres is actually not ideal for write-heavy workloads. I'll discuss this in details later. But for the OpenAI's read-heavy workloads, it can scale really well. So there are some known challenges in the write-heavy workloads. First of all, I think Postgres MVCC design, which is the multi-version concurrency control. Postgres MVCC design has some known issues. It's not very efficient. There are several issues. The first thing is it will cause the table and index bloat. Another thing is that it will also increase the auto vacuum tuning complexity, and also the version churn. Also, there also have the version churn from triple copying, and also it increases the index maintenance overhead. If you want to learn more about that, Andy and I wrote a blog article in 2023. The title is the part of Postgres we hate the most. We discussed the MVC design in details and the issues it has. And also for the write-heavy workloads, it's also difficult to scale to read replicas. One thing is that write-heavy workloads can generate lots of red hat logs. So those red hat logs will be shipped to the replicas. If you have lots of the rats and generate lots of red hat log, the high volumes you need to ship more data to the replicas. It can potentially increase the replica lag in the replicas. Another thing is that the problem even get worse when you have more replicas because the primary need to send the same copy of right hat log to many replicas. If you have many lots of replicas, the network bandwidth can be a bottleneck. That's why the heavy workload can change in Postgres. So after we migrate most of the heavy workload from Postgres, currently the really heavy workloads are still served by the unsharded Postgres in Azure. The problem is how. The question is how. How can we just serve the OpenAI's really heavy workload in just in a cluster with just a single primary instance? We did lots of optimizations here. The first thing is that we try to reduce the load on the primary because we only have the one primary. We want to reduce the load as much as possible. Uh, i- Particularly, we want to reduce the load from both writes and reads. For the writes, we want to mitigate the write spikes in primary. So the writes, the first thing we did is that we migrated write heavy workload from Postgres to our systems, and also we reduce the number of writes at the application level because we also identify some bugs in the application side which generate unnecessary writes. So we carefully optimize the application to make sure it only writes to Postgres when necessary, and there will not be any like duplicates or unnecessary writes in the application. The start thing we did is that we also use daisy writes where possible to smooth out the write spikes, to avoid the spikes and smooth it out. The last thing we did is that another thing we did is that we also when backfilling a field, we also strict limit the backfilling. Usually it means that it may take us a week to backfill a field for our table, but it's really necessary because if you don't really limit the backfill, it will cause the write spike in Postgres, which can cause lots of issues. So when backfilling a field in Postgres tables, we will set the read limit on that. That's what we did for the writes. But for the reads, we also offload read queries from primary to read replicas because we want to offload uh, uh, the read query from primary whenever possible to also reduce the primary load. Because we only have one primary, if there is a read queries, I think if we can move to read replicas, we will not uh, we will not read from the primary. Some reads cannot be moved due to transactions. So for those queries which are required to stay on the primary, we want to make sure those queries are efficient in primary. Another thing we did is the query optimization. We optimized the queries allowed to avoid anti-query anti-patterns and also avoid non-running queries. So non-running idle queries can cause lots of issues in Postgres. It can be auto vacuum and consume lots of resource. We avoid long-running queries by setting timeout on different levels. Um, we we set the idle instruction session timeout. That's a parameter in Postgres, will kill the queries if it's idle in the transaction for a long time. We also set the statement timeout because sometimes we find some queries actually idle in a transaction, but the status is active for some reason. So which means the idle instruction session timeout will now kill those queries. That's why we also need to set the statement timeout. In the meantime, we also set the client side timeout in the application. So if there are like some request is longer than a threshold, will in the application it will also kill that request. We also avoid OLTP query anti patterns because we observe multi-way joins in Postgres queries. Um, and the most expensive queries will join actual 12 tables together. It's super expensive, and here previously, we had a search on search queries, and it actually led to a save in the past. So we want to avoid those expensive multi-table joins queries in Postgres because it's not a typical LTP queries. To avoid those expensive multi-way join queries, we actually modify the application code to make sure it to break down the joins in the application side. So instead of joining 12 tables in the Postgres server, we just did it. We joined in the application so that Postgres queries will be still efficient. And in the application, I think we optimize on application level to make sure we don't have such expensive query in Postgres. Another thing we notice is that yeah, users don't write raw query, SQL queries in Postgres. They usually use ORM, but developing with an ORM can easily lead to inefficient queries because when writing with ORM, you don't know what's the query generated by the ORM. So usually it has some bad queries. So this requires the developers to carefully write the code using ORM to make sure it won't generate the bad queries. Another challenge we face is the single point of failure. Because the primary instance, there's only one primary instance. It can be a single point of failure. So if the single that single primary is down, if that instance goes down, no writes will be performed. Because we only have one writer, so no writes can be performed anymore. But we have many read replicas. So if one read replica fails, applicant can still read from others. Um, so we have single point of failure on primary, but not for read replica. So in the application side, we make sure that most critical requests actually read only, and they only need to read from replicas as they don't need to write or read from primary. Which means that even if the writer goes down, those critical requests can still operate by fetching data from replica. So it usually will now cause the severe issues to our users. So if the primary goes down, it will be a sub 2 instead of a sub 0 or sub 1 because of the most critical requests can still operate by reading data from replicas. So in this way, we can mitigate the impact of the single point of failure from primary. So besides that, we also categorize the request by priority. So the idea that some requests have high priority and some requests have low priority. So high priority requests will have a greater impact on users when they are unavailable. So it will cost sub 0 compared to the low priority, which will only cost sub 2. So we categorize the requests by the high priority versus low priority. And the next step is that for the high priority request, we want to make sure we have the dedicated replicas for those high priority requests to prevent them from being impacted by other like low priority requests. So idea that if there are some expensive queries in a low priority request, it will not impact the high priority request. So for example, if there are a spike in the expensive queries in the low priority request, they only affect the low priority request because we have a dedicated replicas for high priority request. So this can help us like avoid the outage, the sub 0, when there are issues in the low priority request. We also need to read limits. We also have read limit in different places. This is because a search from a single expensive query, as we discussed before, can bring down the entire service. So previously we had some expensive queries running on primary. For example, there was a 12 join queries, and typically the volume was low, so it's okay in the most of the time. But the issue is that sometimes there will be a sudden spike in one of those expensive queries, and it can took down the entire instance. So in the past set, we had such a spike in the 12 John query, and the CPU usage jumped from 20% to like 99%. And eventually the whole instance was down because of this single query. So we want to have some rate limit to help to mitigate this case. So we have rate limiter on different level. The first level is that we have is the application level. So we rate limit the application level functions to reduce the loads during the peak traffic. So idea is that for the application requests, we should have rate limit so that we don't have a spike from a specific users or specific region. Another level is the new is on a new connection. We also rate limit on the creation of the new connection because it's also super important for us to prevent connection pool exhaustion. So in the past, we saw some like the huge number of connections. It caused several lots of issues. So we also rate limit the creation of new connection to make sure the connection pool is not exhausted. We also rate limit for specific query digest. This is because the past the incidents we had, so the whole service was took down by a specific expensive query. So we have a feature to limit on specific query digest. So if the some queries, if that issue happen again, we can block the query entirely or set limit on specific query so that it will not eat a lot of results and break take down the whole service. Connection pooling is also super important because previously we had some set like I running out of the connections from Postgres. Um, so yeah, in the old days we even don't have a connection pool, and yeah it's very easy to have the connection these options. So right now we are using PgBouncer as a Postgres proxy. It acts as a connection pool, which enables a connection reuse. The idea is that the connection can be reused by different applications. You don't need to close and open the connection again and again. So the connection can be reused. Um, this can significantly reduce connection latency. From our experiment, it can basically reduce like connection latency from like 50 millisecond to less than 5 millisecond. That's a huge improvement for creating connections. Uh, it also reduces the number of connections because those connections can be reused across different applications. This is super important for us given we have like 5,000 connection limit on primary, and there's a hard limit on the Postgres instance, and we cannot increase that limit. So we need to use those connections carefully, um, and connection pool and PgBouncer help us. And it's also responsible for fail or to fail over. So if the replica fails, sorry, not fail over, but if a replica fails, the traffic will be automatically routed to other available replicas through the PgBouncer. Another super important aspect is the about the schema management. Because if you don't do it correctly, you might have some like expensive rewrite, full rewrite for the entire table, which can cause lots of issues. So for schema, we need to do it very carefully. So at OpenAI, only that with schema changes are allowed. Um, so first of all, we don't allow creating new tables or introducing new workload in Postgres, because we don't want to add the new red traffic in in the current setup. So because the current setup does not scale the REST very well, so we don't want the new red traffic in this setup. We also allow adding or removing columns in tables with the 5 seconds timeout. So any changes that require a table rewrite are not allowed. So for some schema changes, for example, when you alter a column type, it might need to adopt an entire table and rewrite the whole table. It will basically interrupt your production workloads. We definitely don't allow that. So we only allow some that which metadata change, like adding a nullable columns or remove column, which will typically finish within a second. We only allow those operations. So for adding columns, we only allow adding nullable columns. Otherwise, it may have some it may cause some full rewrite for the entire table. For example, if you set for the when adding a column, if you set the default to a dynamic variable, it might it might trigger rewrite for the entire table. So for adding a column, we also require the column be nullable. We also allow adding or dropping indexes concurrently. Um, One thing we found is that schema change can be blocked by some consistent queries. Um, so in a long running queries, when the query running longer than 1 second, if those queries are consistent present on the target table, the migration may fail because those queries will block the schema migration. Um, what we found is that so to find those queries, we basically run the SQL on the PgStack activity. The query is the stack star from PgStack activity. We'll query like your target table name and the duration is longer than 1 second. We run this query periodically, and if some queries like consistent present, it means that those queries are actually blocking the schema migration for that on the target table. Um, so if we find those queries, we can either fix those queries in the application, like to optimize queries to avoid those query consistent to avoid those long running queries, or we can move them to replicas so that it will unblock the schema migration on the primary immediately. That's it from my talk. So overall, I think we are after all the optimization we did, we are super happy with the Postgres right now for our read heavy workloads. It's really scalable and reliable right now. I think in the past 6 months, we don't have any sub zero regarding to Postgres. We do have one sub zero, but it's because of we have a sudden spike of the write traffic. Um, and besides that, we don't see any sub zero on Postgres instance. So I think the lesson is that for write heavy workload, uh, Postgres might not be suitable, but for read heavy workload at OpenAI, if you optimize it carefully, I think it can scale the OpenAI's workload, read heavy workload to a very large scale, even with a single primary multi-replayer architecture without sharding at all. Thank you.